Okay, so in that last example, we had a graph that when the value of x was 0, so when we played 0 games, it ended up costing us $3 to rent the shoes. There was a constant, and that constant made it so that 0 games still cost $3. That is what's called partial variation. So in the first example, we went through 0, 0, and that was direct variation. If you get 0 toppings on your pizza, you're not buying a pizza, you get 0, then the cost of toppings is 0. You don't have to pay a constant. But in the second example, the bowling question, we had a $3 constant for the shoes. And so when we went 0, 3, that means that we're not going through 0, 0, and that is a partial variation. So anytime your graph does not go through 0, 0, it is partial variation. If it goes through 0, 0, direct variation. Now we have one more question to do, and it involves an equation and subbing in. So the equation is the value of a car is equal to 24,000 minus 1,500 t. So the formula, the value of the car is 24,000 minus 1,500 t, where t is the number of years after it is purchased. So if this car was purchased, right now, time would be 0, and the value of the car would be, well, 1,500 times 0 is 0, so all you're left is 24,000. At the very beginning, this car was worth 24,000 before you drove it off the lot. So that's the value at 0 time, $24,000. That is not going through 0, 0. This is an example of partial variation. Now, the question says label the variables and use the equation to determine the value after 7 years. So first of all, we need to label the variables. The value of the car is what we're measuring. We want to know what the value of the car is. So that is dependent. So the y, typically, in this case, is a v, but in most cases, it's going to be y equals mx plus b, and the y is dependent. And that's also the y-axis. That's why we use y. So that's the dependent variable. We have a constant of 24,000. That's how much it was, the car is actually worth when it's brand new. And then minus 1,500 t. And the t represents the independent variable. It's the one it's changing. So the independent variable is the t. That is changing predictably, and it's going to change the value of the car. So the value of the car is dependent on the time. And typically, we put our independent variable at x. So it's at the x axis. Dependent is y, independent is x. That is the situation. Now, we've labeled it. We can also go further. Your years, the number of years, looks like in this case, it's whole numbers. So that's going to be discrete. And then the value, it looks like it's all whole numbers right now. So that's also going to be discrete. So a whole number, no decimals, discrete. If it has decimals, it is continuous. Last thing we need to do, we need to predict the value of the car or determine it after 7 years. So we need to sub in 7 years, 7 for t. So I'm going to do that now. We've got the value of the car is equal to 24,000 minus 1,500 t. So again, there's the t, but instead of putting a t in, I'm going to erase that and I'm going to put the number 7. So That's because there's 7 years. Grab a calculator, and I've got 24,000 minus 1,500. I get 13,500. Okay, so 13,500, that's the value of the car after 7 years. And you need to remember bed mass. So if you're going to solve this, it ends up not having to be a factor because it's going to multiply first anyways. Your calculator will follow bed mass, but make sure you're following bed mass and following all the other rules that we've kind of established when you're solving. But this is just a simple sub in and solve. All right, the set of questions for this is page 146, numbers 1, 2B, 5, 9, and 11. So there's the set of questions for that part. We're going to continue on with the second half of the lesson momentarily. Okay, so hopefully you completed your homework, and if you haven't yet, I would take a break, pause this, go do that work, and then continue on with the second part of this lesson. So the second part, we've already kind of touched on it, is going to be all about slope, or what's called rate of change. So they're the same thing, and essentially what you're looking at is a ratio of how much the dependent variable, the y, changes for every change in the x. So the equation is change in y divided by change in x. And we'll get a look at that. So we've got there's the There's the first equation that you needed to know, is that triangle is a change in y divided by change in x. So another way of looking at that would be to talk about rise over run. So the other way of looking at it is rise over run. And if you have 2 points, you want to know the rise over the run. Rise over run. So that's another way of looking at it. We're going to get into some detail with that. There's a lot of visuals on your handout that is posted on D2L. So that's a good spot to start. Obviously, you should be, working through that while listening to the video anyway, so you're just filling it in, and there's lots there. But the way that this is going to start is actually table of values. So one of the ways that you can identify if a relationship is linear is just by looking at the table of values. And so I'm going to do my first example of a table of values now, and we'll continue. So we've seen this already. There's a table of values. We've got values on the x going all the way from 0 to 4, and then on the y from 0 to 48. First of all, it goes through 0, 0, so that would be what type of variation? That would be direct variation because it goes through 0, 0. All right. Now, the next part we're going to do is figure out the slope. So we've got 0, 0, and then on our second value, so in this we've got nothing to do here because we can't really tell, but in this one, what we need to do is we take the 12 minus the value above it, 0, which is equal to 12. So 12, the value in that space, minus the value above it, equals 12. The second one we've got is 24. So we're going to take the 24 minus the value above it, which is 12, which is also going to equal 12. Next, we've got 36 minus the value above it, which ends up being 24, equals 12. And last one but not least, 48 minus the 36 equals 12. And because they equal 12 every single time, we're just looking at the y values and subtracting. So the y value minus the one above it, and if it's a constant, so same number every time, 12, that makes it a linear relationship. And in that case, the slope ends up being 12 divided by, if you look over here, the x's are going up by ones. They're always going up by ones, so it's 12 over 1 or just 12. 12 over 1, 12 over 1, they're always 12 over 1. Constant rate of change, constant slope of 12. All right, now the next example on your handout is a little different. We've got values of 23, 15, 7, negative 1, negative 9, negative 17. First of all, you should notice that those values are going down. So that's what a negative slope looks like. It's the values are going down instead of up. And also take a look at the x values. They're not going up by ones, so that's going to change the slope as well. The process is exactly the same. So to take a look, you've got the very first value, 23, and in this space, you can't do anything. But on the next one, you've got 15 minus 23 is equal to negative 8. So your very first one, 15, and the one above it, minus 23, equals negative 8. Now the next one is 7 minus 15 is equal to negative 8. Negative 1 minus 7 is equal to negative 8, you guessed it. And negative 9 minus 1, negative negative, makes an addition. 9 plus 1 equals, negative 9 plus 1 equals negative 8. And negative 17 minus 9 is negative 8. So negative 8 every single time, and that's great, except your slope, the x's are going up by 5s, so you've got to go negative 8 over 5, over 5, over 5, over 5, and over 5. That is your slope. It's over 5 because x's are going up by 5s. So rise over run. In this case, the rise, the y, is actually going down. So it's a negative rise. It's a negative slope. So negative 8 over the run is 5. Okay?